So now we're going to take the lesson we just saw from the voltmeter affecting the circuit and look how it happens with a PIC microcontroller. The PIC microcontroller is what's on the USB bit whacker, and we're going to see why you want to have a pull-up resistor to begin with, and see what values we choose for those for that resistor. Okay, so if I have a PIC, which I'm going to represent by this rectangle here, it has an input line, or something we're going to select as an input line. It's N1. Now, basically what that means is inside your PIC is something like a crude voltmeter. That's one way to think about it. And it can only measure 0 or 1. And it's comparing the voltage coming into that input pin to the voltage of the PIC, VCC. And if it's close to that same voltage, it says it's 1. If it's not close at all, it says it's 0. So you can think of it as a voltmeter. You can think of it as actually having the same sort of internal resistance as a voltmeter does. Now, you actually get the real value from the spec sheet on the bit whacker from the PIC. Here we're going to just assume it's 1 mega ohm for convenience. Now suppose that I have nothing hooked up to this pin. Well, with the PIC, there's so much stuff going on. There's these megahertz signals going through, and as we know with capacitors, you can induce a charge that way. There's some inductance going on, all sorts of crazy things. So if you just let the pin float, you don't tie it to VCC or to ground, you can have an indeterminate value. It can be 0 or 1 at any given time. So let's see what we do about that. First thing, we can actually just tie it directly to VCC. Now this is fine, you would think, but so it's going to measure 1 all the time. Great. But this is a PIC except for input. What happens if for some reason a programmer accidentally wires that same PIC, that same pin, to output? Well, let's look what happens inside the PIC. So if I have this as output, and I see we're going to VCC here already. Now basically I have a switch. And the switch can either be thrown, be flipped up to VCC, or it can flip down to 0, to ground. Well, if the programmer flipped the output, the pin to output, and then flipped it to VCC, well, we have VCC to VCC, there's going to be no current flowing. It's basically the same voltage level, so nothing's going to flow. However, if the programmer then flips the output to 0, suddenly we basically have a short circuit. We're going from VCC to ground through the PIC. Well, that's the problem. These microcontrollers can only take so much current flowing into them. And you're almost guaranteed with this, with any sort of power supply, that you're going to kill the microcontroller. So, can we do something more intelligent? Well, we can certainly put a resistor in here. A resistor would actually save it. How big a resistor do we need? Well, let's assume that the PIC can handle a 20 milliamp input current. So, and this is just for one pin. And we're going to do voltage at 5 volts. We need to limit the amount of current going through here, but we know how to do that. It's just simply Ohm's law. So we know that V equals to I times R. In this case, we're trying to find R. So, pretty quickly, 20 millivolts over 5 volts. Oops, I'm sorry, it's the wrong way. R equals V over I. Let's try that again. 5 volts over 0.020 amps, which is going to equal to, let's see here, that's going to be 250 ohms, I believe. Make sure I did that right. 2.5 and 2 decimal points is out. Yep, 250 ohms. So in theory, if I just placed a resistor here of 250 ohms, it would be sufficient to keep that one particular pin from shorting out. But the PIC here has 13 to 16 pins that can come in. So not only does it have a certain amount of power it can handle per pin, it's a certain amount of power it can handle overall. So let's think about this for a second. If I had a PIC and each pin was doing 200 milliamps, how much power is coming in through each pin? Well, we know power equals V times I, or in other words, 0.020 amps times 5 volts, which equals, let's see here, that's 0.1 watts. Okay, that's fine. But suppose I then have 16 input pins I do this to. So now I have 16 pins, each doing 0.1 watts. And we end up with 1.6 watts of power going through this little microcontroller. There's a good chance that microcontroller is going to burn up. So generally, the spec sheets for a microcontroller both say how much power it can handle per pin and how much power it can handle overall. So a typical thing for this might be, say, a watt or a half a watt. Let's just say 1 watt for convenience. So suppose the overall, so all 16 pins, so power total has to be less than 1 watt going into the PIC. Well, fortunately, we don't really care about maximize the amount of power coming in. We just want to pull up a resistor that will make sure that that when we're actually doing the input here, that we get a value of 1. Okay. Well, thinking about that for a second, I'm going to choose, oh no, something larger, something where I don't have to worry about this. Let's choose a resistor instead of 250 ohms. Let's choose a resistor for a pull-up to be 10,000 ohms, 10K ohms. Okay. Well, how much power is that going to bring in? Well, we can, using our formulas from before, we know that I equals V over R. And so we can do the formula directly. No, I have enough space here. So we're going to have 25 10,000ths of an ohm, of a watt. There we go. And so now if I have 16 pins coming in, it's not going to be a problem at all. I'm going to still be in the milliwatt stage. Okay, great. So we'll go with, going back to input, we'll choose a value of 10 kilo ohm. Okay. Now, that makes sure that we actually have a safe value for a resistor here. And it doesn't matter if the if the programmer changes to input or output, we're still in good shape. Now, note that we could actually make the resistor even larger if we wanted to save more power. But this tends to be a relatively good value. We're not wasting much power, and we're going to be pretty sure that it's going to pull up the pin to VCC.